Hello, welcome again. We are solving some questions of theory of machine design. The topic is friction in screw, bearing and clutches. Question number 6 is in a screw jack the diameter of threaded screw is 40 mm and the pitch is 8 mm. The load is 20 kilonewton and it does not rotate with the screw but is carried by a swivel head having a bearing diameter of 70 mm. The coefficient of friction between swivel head and spindle is 0.08 and between screw and nut is 0.1. The efficiency is given by option A 40.1%, option B 20.9%, option C is 55.1% and option D 28.1%. So here the helix angle is given. First of all, we calculate what is angle. So helix angle of a screw is your is can be found like this: tan alpha is equal to P by pi d. So P is your pitch, D is diameter. So helix angle P is given as and diameter is given as 40 mm. So alpha comes out as 3.64 degrees. Okay. So helix angle of the screw jack is here 3.64 degree, or it can be considered as an inclined plane angle when the screw rotates by a rotates 1 turn or moves by pi d horizontally, then the load moves up by a distance of pitch. And now the coefficient of friction between the screw and nut is zero point 0.1. So the angle of friction between the screw and nut is at 5.7. So now the torque required to raise the load when the rotation of the load is not considered, as it means the load rotates with the screw, is given by T1 is equal to F into R, that is W tangent alpha plus pi R. So here F is the force applied at the circumference of the screw when load does not rotate with the when load rotates with the screw. Okay. So now as so torque T1 is used to move the load up. When only T1 is applied, load rotates with the screw. Okay. Load rotates with the screw. Okay, now we have to prevent the rotation of load, so there is a bearing between the load and screw. So that bearing will not rotate with the screw because of friction between the screw and bearing. Okay, so the so we have to overcome this friction also, and some torque has also been consumed in this friction also. That torque is given by mu WR. Mu is coefficient of friction between the bearing and the screw, and R is radius of the bearing. Okay, so T2 is your R is your radius of the bearing. That is your 0.08. Okay, and W is your 20,000, and R is your point. Here R is your diameter is 70 mm, so radius is your 35 mm. That we now will take the coefficient of friction between the bearing and screw and radius of bearing. Okay, so that comes out torque T2 comes out as 56 Newton meter when the polar friction is considered. Okay, so that is the torque required to overcome friction, and that is the torque required to raise the load with rotation. So total torque required is T1 plus T2. Okay, so that is 121.86 Newton meter. Now in this question we have to calculate the efficiency. Efficiency is given because here rotation of the load is prevented, and bearing is and there is bearing, so we cannot use that formula because here the rotation of the load is considered. Okay, so we will go by step to calculate this efficiency. So efficiency is output work by input work. Okay, so work done in lifting the load per revolution divided by work done in by applied force per revolution. That will be your efficiency. So as load in one revolution the load is lifted by amount P, so that is the work done in one revolution. Okay, suppose now here this F was the force required at the circumference of the screw when rotation of the load is considered. Okay, now suppose there is new app is suppose F1. F1 is the force required at the circumference of the screw considering both polar flexion and friction between two nuts. In this, the polar flexion is not considered. Okay, so F1 is the force required at the circumference of the screw considering both polar flexion and friction between screw and nut. Okay, and if F1 is applied at that point, okay, and then it will for p distance it will travel a distance, screw will travel a distance of pi d. Okay, so now this p by pi d is again tangent alpha, so F1 is your p by r, because p sorry, w we have 20,000. Okay, and now we need this F1. Okay, this F1, so F1 is your total torque by radius of the bearing. So radius of the bearing is radius of the screw, because F1 is at the circumference of the screw. Okay, so total torque is your 121.86 and radius is your 0.02. Okay, so that radius is now radius of nut. Okay, or radius of screw. So that F1 comes out as 6093. Now we can put the value, that is 20,000. W is 20,000 and F1 is your 6093 and this is your tan alpha is your 0.0637. Okay, so it comes out as 0.209 or 20.9%. So option B is the